we've been playing around with Gaussian processes for a while now, and at this point you may be wondering, hey, these Gaussian processes seem kind of cool, but are they really good for anything? And what does this have to do with machine learning anyway? And as you may have guessed, I'm about to tell you that Gaussian processes are a very powerful tool for regression. Now, something I'd like to make very clear right off the bat is that for regression, or really any practical application of Gaussian processes, we're always sort of in the trivial case of a Gaussian process, because we're only looking at finitely many points. So maybe we have some points xi, and maybe there's some yi's, and we want to look at the value at a new xi, predict the value. That's what we're doing in regression. And so here we only have these finitely many points, and since a Gaussian process is just a multivariate Gaussian on any finite number of points, in fact, we're just in the trivial case. It's just a multivariate Gaussian. So that's something which is very important to keep your eye on, or to remember about applications of Gaussian processes to regression, is that really it all just boils down to the basic properties of multivariate Gaussians. So in some sense, to me, it's kind of overkill to refer to this as Gaussian process regression, because it's not really using the full force of Gaussian processes. Gaussian processes, like if this is R, then a Gaussian process would be a collection of random variables defined at every point of R. And that's not what's going on in this application to regression. It's not really using, maybe in some sort of indirect way we're defining these things, but we're not really using any of the fundamental sort of analysis that goes into analyzing these real sort of most general forms of Gaussian processes. Okay, so because of the fact that we're only looking at these finitely many points, it turns out that actually Gaussian process regression is, in some sense, in a very real sense, it's actually essentially the same as Bayesian linear regression. In Bayesian linear regression, we had some finite number of points, and we put a prior, and then so we had some multivariate Gaussian distribution, and then we're just doing inference in that multivariate Gaussian distribution. And mathematically speaking, it turns out that Gaussian process regression and Bayesian linear regression are essentially mathematically equivalent. But the twist with Gaussian processes is that they use the kernel. They use the kernel instead of using basis functions in order to define the family of functions that you are using for regression. And so that twist is actually a very, very nice, very powerful twist, because using kernels allows us to define a very rich family of functions that just using basis functions alone could not handle. So that's the twist arising from kernels, the sort of kernel trick. Okay, so to start out, let's actually start talking about Bayesian linear regression, and then we'll see how Gaussian process regression arises very naturally by thinking along these lines, starting with this and then thinking about how to use the kernel, thinking about this as a Gaussian process regression. Okay, so in Bayesian linear regression, the setup, is we have some data, some x1, y1, up to xn, yn, and xi is in rd, and yi is in r. And the model for Bayesian linear regression is that we model these y's using random variables, y1 up to yn, and these are independent given some parameter vector w. And the distribution that we put on these y's is, we say that the density of yi is given xi and w is a univariate normal with mean w transpose xi and some variance, let's say sigma squared. And now you could use basis functions here. I'm I'm going to omit using basis functions because using basis functions, if we were to define, x tilde as the image of xi under phi, then we can just replace this with x tilde and everything just works out the same. So it's really not that important to think about basis functions. We can just think about this special case here, the linear, sort of linear in x case. And then continuing our definition of the model, we have W in Bayesian linear regression. We put a prior on W, and we put a multivariate Gaussian prior. Usually we take mean 0, and let's say variance. Let's say the covariance is just a spherical, so it's a spherical Gaussian with variance v in each coordinate. So v is just some positive number here. Now, another way we could have written this part here is we could have written this as yi equals w transpose xi plus epsilon I, where each of these epsilon i's is a normal with mean 0 and variance sigma squared. So that's just another way to think about this. And they're all independent and independent of w. Okay, so what do we know from, what can we conclude from this? Well, w is a multivariate Gaussian, and so let's think about this function w transpose xi, or w transpose x for some arbitrary x. Well, since w is a multivariate Gaussian, then this is a univariate Gaussian, right? For any x in Rd, w transpose x is a univariate Gaussian. Univariate Gaussian, just from the definition of a multivariate Gaussian, because this is a linear combination of the entries of this multivariate Gaussian, and therefore it's univariate Gaussian. And in fact, it turns out that this thing, if we think of it as a function of x, if we think about the collection of all of these univariate Gaussians that we get as x ranges over Rd, this is in fact a Gaussian process. So now we start to see where things are going. So this, let's call it Zx. We've been using Z for a Gaussian process. Zx, which is, let's switch it. Let's swap it around and call it x transpose W, is a Gaussian process on the set S where S is Rd. So the collection of these random variables as x ranges over Rd is a Gaussian process. And let's verify that. It's easy to check, so let's just check that. So in order to check that, we need to let, maybe I'll switch colors here. Let x1 to xn be in Rd. And what do we need to show for it to be a Gaussian process? We need to show that all its finite dimensional distributions are multivariate Gaussian. So we let these points, and we're going to look at the finite dimensional distribution on zx1 to zxn. So we need to show that this vector is a multivariate Gaussian. So what is this? Well, let's just plug in the definition of what these things are. And now what can we do? Well, we can factor out W here, so let's do that. We can factor out, we get a matrix now, x1, a matrix with rows x1 transpose to xn transpose, times this W vector. W is our multivariate Gaussian. And let's call this matrix A. Let's give it a name. So this A, actually this is what we called the design matrix earlier in the context of linear regression. So this is nice. So this vector here is just the design matrix times W. And since W is a multivariate Gaussian, then by the affine property of multivariate Gaussians, we know that this A times W is also a multivariate Gaussian. So this is Gaussian by the affine property. If you don't know what I mean by the affine property, you can watch the videos I have on multivariate Gaussians and see why this is also a multivariate Gaussian. Or at least, I don't think I proved it, but at least we state the result. Okay, so that means, since AW is a multivariate Gaussian, that means that this is in fact a Gaussian process. And let's think about what this thing actually is, right? I mean, what does this Gaussian process look like? Well, if we think about it, it's this collection of random variables, and if we think about it for a fixed W as a function of x, then as a function of x, this is a linear function, right? This is just some linear thing for a fixed W. So this is just a plane, right? So you might guess that as if we were to successively draw samples of W, we would get a different plane for each of these, and you might guess that in fact that this is the random planes Gaussian process that we saw before. This thing, remember here? So we had in our examples of Gaussian processes, one of them was this in the 2D case. One of them was this for this what I call this linear kernel. It gave us all these random planes. So I'll draw some samples from this maybe. It's kind of slow. My code is probably inefficient. So each of these is a sample from this. And each of them is a plane. It's linear in x. So let's check that. Let's see if that's actually true. Let's see if that is the particular Gaussian process that we're dealing with. So first, let's compute the mean function for this Gaussian process. The mean function, mu x, is just the expected value of the Gaussian process at each given x. And so this is expected value of x transpose w, and by linearity of expectation, it's equal to x transpose EW, and w has mean 0, so this is just 0. So that was easy. And now let's see what the covariance function is, maybe in a different color. Let's call it x prime, because I'm using y for something else above. So the covariance function, well, what's the definition is just, it's the covariance of zx with zx prime. And the covariance of this we can write as expected value of zx prime minus the product of the expected values. And from here, from above, we know that each of these expected values is 0, so this is just 0, it goes away. And now we need to figure out what this is. So let's plug in what these random variables are. It's the expected value of x transpose w, x prime transpose w, and let's flip that around actually, bring the w's together, so we get w transpose x prime. And now again, by linearity of expectation, we can move the expectation in here. This becomes the expected value, so this x transpose times the expected value of w transpose times x prime. You can check that this is a valid operation. Actually, you can check that. This is just this is just like you can think of it as a quadratic form here. This w transpose is a matrix, and so by the linearity it just moves through that sum, and you get this. So that's, you can check that if you're not too sure. I would encourage you to check it if you're not too sure. And then what is this? What is this expected value of w transpose? Well, whenever you see this kind of quantity, one thing that you can do to compute it is to use the covariance of W, the covariance matrix of W, because the covariance matrix of W is the expected value of W transpose minus the expected value of W times the expected value of W transpose. This is a super handy formula for the covariance, for proving things about the covariance. Now note that since W is a column vector, each of the, this is a matrix and this is a matrix. Okay, so, and then this, the mean of W, is 0, right? That was the mean of W. So this is 0. Need some more space. This is 0. And so this here is just the covariance of W. And what is the covariance of W? VI. So we get, maybe I'll keep the orange for now. So this is X transpose VI, X prime. And let's go ahead and pull the V out. V is just a constant. And we get V X transpose X prime. Beautiful. Nice and simple. And so, in fact, if we go back over here to our MATLAB, this is, in fact, the Gaussian process that we were dealing with before, because it has this kernel, what I was calling this linear kernel. X transpose Y. And you can change the constant here to any non-negative constant. So this is that V constant. All right, very nice. So let's think now about, so that was we started with Bayesian linear regression, and we observed that the function here that we're using to do the regression is in fact a Gaussian process. And now we know that one way to generalize this type of linear regression model is to use basis functions, right? So we can map the xi's to some other, using this, well, maybe to R, M or something, using some nonlinear functions, phi, and in that way we can model more complicated nonlinear effects in the xi's. But it turns out, so what that would do would be essentially it would give us a new function here, right? That would give us a new function, something more general. That would of course also be a Gaussian process, but the key idea, the main observation of Gaussian processes is that in fact we can generalize this to an arbitrary Gaussian process, z evaluated at xi plus these epsilon i's, and that in this more general formulation we can still do efficient inference. Well, it's at least as efficient as in the Bayesian linear regression. Mathematically, it's the same inference. In a Gaussian process regression model, you just replace these functions with your arbitrary Gaussian process, and then mathematically the same exact inference that you do in the Bayesian linear regression works in the Gaussian process. And so this is the key observation. And the advantage of this over just using basis functions is that in a Gaussian process you can effectively some Gaussian processes have effectively they correspond to basis functions mapping into an infinite dimensional space. So of course you could never actually compute such a basis. You could never actually do it. And yet by using the kernel you can actually do inference in such a model. And so you can get an extraordinarily rich class of functions to do regression with when you're using Gaussian processes. And so that's the win of Gaussian processes. All right, so next we're gonna see how to actually do inference in this model. And this will generalize the inference for the Bayesian linear regression, but we're gonna do it in an easier way than we did before when we did Bayesian linear regression. Okay, so that's gonna be cool. See ya.